Okay, in this class we discuss the probability densities of finding the electron in the hydrogen atom. This probability density of the electron depends on two sets of variable. One, it depends upon the radial variable, and secondly, it depends upon the angular variables theta and phi. So we will discuss these probability densities in two sessions. In today's class, we consider the radial probability densities. Radial probability density means what is the probability of finding the electron at a particular radial distance away from the nucleus, okay, or a particular region away from the nucleus at a fixed radial distance. So let us start with the wave function. We know that the hydrogen atom wave functions, it depends upon, we are using spherical polar coordinates. So this wave function depends on the three quantum numbers: principal quantum number, orbital quantum number, and magnetic orbital quantum number. And we are using spherical polar coordinates. So we can write this wave function as product of three wave functions. One is the radial wave function. It depends on both n and l. And second is the wave function theta, or we can say polar wave function. It depends on the polar angle theta, and this is decided by two quantum numbers L and ML. And finally, the azimuthal wave function, which depends on the azimuthal variable phi and depends on the single quantum number ML, M suffix L. Okay. Now, if we find the probability density, we have to take the mod square of this wave function, which means the mod square of each of these wave functions: radial wave function, polar wave function, square of polar wave function, and square of azimuthal wave functions. Okay. Now, suppose we want to calculate the probability of finding the electron at a volume element, in a volume element dV. Then this is probability density. So in a three-dimensional system, probability density means probability per unit volume. Okay. So if we want to find the electron in a volume element dV, what is the probability of that? It is psi square dV. Probability per unit volume into the volume element dV. So we can multiply this with dV. So this is r square into theta square. Theta depends on small theta square phi square, multiplied by the volume element. This volume element, if we use spherical polar coordinate, this volume element is r square sine theta dr d theta d phi, where r is the radial distance, radial variable, theta is the polar angle, and phi is the azimuthal angle. And this is the volume element, r square sine theta dr d theta d. This is the volume element in spherical polar coordinate. Okay. Now suppose our aim is to find the probability of finding the electron at a distance. Let us say, suppose this is the position of the nucleus. Okay, consider a radial distance r from the nucleus. Okay, and we can think about a spherical region of radius r. Okay, now consider a further distance dr, a further distance of length dr. So let us consider this spherical shell of radius r and thickness dr. Now suppose we want to find out what is the probability of finding the electron in this shaded region. Probability of finding the electron between r and r plus dr. Okay, at a distance nearly r from the nucleus within an interval dr. What is this probability? Now let me use the simple p r dr for this. Okay. So this is the probability of finding the electron at a distance between r and a radial distance between r and r plus dr from the nucleus. Or we can say probability of finding the electron approximately at a distance r from the nucleus. But since r is a continuous variable, we cannot choose a particular r, we can only talk about probability of finding the electron between r and r plus dr, or within a small interval dr around r. How do we find this? Now, in order to find this, what we can do is we can take this probability in the previous steps, that is psi square dV. It is the probability of finding the electron in a volume element, right? Now, what is the probability of finding the electron between r and r plus dr? Then we are not worried about, we are considering all possible positions which is at a distance, which is lying at a distance r from the nucleus. Okay, so we are not worried about the angle. So we can consider all possible angles, right? So this probability will be obtained by integrating the above probability psi square dV all over all possible angles theta and phi. Okay, so how do we do this? Let's integrate over, because in order to see, look at this figure. In order to find the probability of the electron at a distance r from the nucleus, we have to consider all possible angles, okay, around the nucleus. So let us integrate over theta and phi. Therefore this equation becomes so if you are integrating over theta and phi, the radial variable, the terms depending on radial variable we can take out, that is r of r square, this depends on n and l, and then there is an r square here, then there is dr here. Okay, the remaining terms are in then first integration over theta. Theta varies from 0 to pi. Okay, 0 to pi, and the terms are theta square, capital theta square, sine theta d theta. Then phi varies from 0 to 2 pi, and here the integrand is mod phi square d phi. Okay, now this each of these wave functions, that is radial wave function r, polar wave function capital theta, and azimuthal wave function capital phi, these wave functions, each of them is normalized. That means here this integral represents the total probability over theta, and this must be 1 since the wave function capital theta is normalized, and similarly for normalized capital phi this must be 1 also. Okay, so if you are assuming that if you are using the normalized wave functions, then the two integrals will be 0. Therefore the probability of finding the electron between r and r plus dr is r of r square, which depends on n and l, this wave function, into r square dr. This is the probability of finding the electron between r and r plus dr. That means within this spherical shell. Okay, within this spherical shell of radius r and thickness dr. So this probability per unit length, okay, the probability of finding the electron between r and r plus dr per unit length, probability per unit length, we can define this as PR. So this is, you just divide this by the width dr. So what you get is r of r square into r square. Now this term is often called radial probability. Radial probability. Probability per unit length of finding the electron around the nucleus over a radial distance r around the nucleus. So this is called radial probability. Now let us look at the plots of radial probability for different states, for the first few states of the hydrogen atom. These are the plots of the first few states, plots of radial probability for the first few states of hydrogen atom. These plots are taken from the third edition of Modern Physics by Kenneth Crane, chapter 7, figure 710. So the radial probability density PR, P of R for the n equal to 1 state, the first plate is n equal to 1 state, L equal to 0. For n equal to 1 state there is only one angular momentum state, L equal to 0. We call it oneness state. In spectroscopic notation this is called oneness state. And n equal to 2, the middle plate is for n equal to 2. For n equal to 2 we know that L has two values, 0 and 1. So L equal to 0 is called 2s state. So this is 2s state in spectroscopic notation. And L equal to 1 state is called p state. So this is 2p state. Okay. And the right plate is for n equal to 3 state. L has three values, L equal to 0, L equal to 1, L equal to 2. Okay. The lightest the blue graph is L equal to 0 graph, that is 2s graph for 2s state, and probability radial probability for 2s state. Then the slightly darker blue is for 2p state, and the darkest blue graph is for 2d, right? 2d state, right? Sorry, 3d state. This is 3s, 3p and 3d. Okay, for n equal to 3 state we label them as 3s state, L equal to 0, 3p state, L equal to 1 and 3d state, okay, L equal to 2. So we can see different variations here. And one more point is the radius coordinate is measured in units of A0, where A0 is the Bohr radius, the radius of the first orbit of the hydrogen atom in Bohr model, which is 0.53 angstrom. So this radial distance is measured in Bohr radius in units of A0. The markers on the horizontal axis show the values of the average radius labeled with the value of L. So these markers here, so they represent the average radial distance. Okay. For oneness state, actually we have done a problem in one of the previous classes. The expectation value of radial distance for oneness state, and its value is 1.5 A0, right? So here the marker is at 1.5 A0. And similarly, such average distance, if you calculate for this 0 stands for 3s state. So 3s state, the average distance is 6 A0 for sorry, not 3s, this is n equal to 2. 2s state, it is 6 A0, and for 2p state it is 5 A0. Okay. For here also the average distance is for 3s state nearly 14 A0, for 3p state nearly 12.5 or nearly 12 A0, we can say nearly 13 A0 maybe, and here it is 3d state, it is nearly 10 A0. Okay, so these are the average, so there is some variation for average radial distance, which we will come back later. And you can see that there are different peaks in the graph. Okay, there is only one peak or one antinode in oneness state. When you come to 2s state, okay, this lighter blue is 2s state. Here 2s state has, there is one peak here nearly at 1 A0, and then there is another peak here nearly at 5 A0. Okay, whereas 2p state has only one peak, the peak is at 4 A0. Okay, here the peak is at A0. Okay, for oneness state. And when you come to n equal to 3, 3s state has 3 peaks, one here and one here and one here. Similarly, 3p state has 2 peaks here, okay, one here and then another here. Whereas 3d state has only one peak, and this peak is exactly at 9 A0. If you drop here, the 9 A0 is the peak. Okay, so first of all, let us ask the question, is there any trend, is there any reason for this variation in antinodes for different L states in a particular, for a particular value of n? Okay, so let us look at it briefly. See, the total energy of the hydrogen atom, we can write this as orbital kinetic energy of the electron plus radial kinetic energy of the electron. Let us for the time being, let us assume that the nucleus is stationary. So we have orbital kinetic energy, and then radial kinetic energy of the electron, and then there is potential energy of the system. Okay, and here this orbital kinetic energy we can write as L square by 2I, where L is the angular momentum, I is the moment of inertia. So the numerator is L into L plus 1 h cross square, and the denominator is I is mr square. Okay, if we assume that nucleus is stationary, this m is the mass of the electron. If we consider that both nucleus and electron is moving, both nucleus and electron are moving, this m is the reduced mass of the two, or reduced mass. Okay, so orbital kinetic energy depends on the orbital quantum number L, and this radial kinetic energy as well as potential energy, this is independent of L. Okay, independent of the orbital quantum number L, and together these two expressions, these two energies, radial kinetic energy and potential energy, together we can call radial energy, because they depend on only on the radial value. Okay, radial distance from the nucleus. Yeah. Now, if we have a particular value of n, for a given value of n, let us say L increases. Okay, L increases. So if L increases, see this expression. Look at this expression. If L increases, the numerator increases. So orbital kinetic energy increases. This term increases. Okay, orbital kinetic energy increases because it depends on L. So if L increases, this part increases. But for a given value of n, okay, total energy is constant, because total energy depends on n, minus 13.6 electron volt by n square. That is the energy of the hydrogen atom. So it depends on the principal quantum number n. So for a given principal quantum number, total energy must be fixed. But for a given principal quantum number, we have different L states, orbital angular momentum states. So as L increases, we know we see that this term, orbital kinetic energy, will increase. Then in order to maintain constant total energy, this part, this together we can call it radial energy. Radial energy should decrease. So when radial energy decreases, that results in a decrease in the antinodes for the radial probability of the electron. Okay, so that is why if you look at here, for example, look at n equal to, for example, consider the central plate, n equal to 2. L equal to 0, this 2s state has 2 antinodes, whereas 2p state has only one antinode. Okay, and when you come to n equal to 3, this right plate, this 3s state has 3 antinodes, 3p state has 2 antinodes, whereas 3d state has only one antinode. So as L increases, okay, this radial orbital kinetic energy increases for a given n, but this radial energy should decrease. When radial energy decreases, there is a decrease in antinodes for the radial probability. Okay, radial probability density, or radial probability we can say. So that is the reason for this variation of antinodes. So what is the conclusion? For a given n, as L increases, the antinodes decrease. For the L equal to 0 state has maximum antinodes, then L equal to 1 state has lower number of antinodes, L equal to, so as L increases, it decreases. And always the highest value of L, okay, for n equal to 1, there is only one L value, L equal to 0. And for n equal to 2, the highest value of L is L equal to 1. N equal to 3, the highest value of L is L equal to 2. The highest value of L will be having only one antinode. Now we are going to discuss 3 different features of this radial probability. Okay, in these graphs we can identify 3 important features. The first of this is the most probable radial distance from the nucleus. We will start with a problem. Let us consider n equal to 1, L equal to 0 state. Okay, that is 1s state. This is called spectroscopic notation. And let us calculate for this oneness state what is the most probable radial distance from the nucleus. And for that we should know what is the this radial, for oneness state, what is the radial wave function. Okay, so the expression for the radial wave function is 2 by a0 raised to 3 by 2, where a0 is the Bohr radius, exponential minus r by a0. A0 is the Bohr radius in as in Bohr model, and r is the radial distance from the nucleus. Okay, so if you know this radial wave function, then what is the radial probability? So the expression for radial probability is radial wave function mod square times small r square, right? So this is equal to, the square of the radial wave function is 4 by a0 cube e raised to minus 2r by a0 into r square. Okay, so this is the radial probability. Then we want to find out what is the most probable, what is the most probable radial distance. So most probable radial distance means the distance, radial distance at which the probability becomes maximum, or the radial probability becomes maximum. So to get that, what we do is, what is the radial distance at which this P of r becomes maximum. So this we can evaluate by finding the derivative of P with respect to P of r with respect to r, and then equate it to 0. Okay, so because when P of r becomes maximum, its first derivative will be 0. So finding this first derivative, we can take constant terms outside, 4 by a0 cube. So we have to find out derivative of this factor, e raised to minus 2r by a0 times r square. Okay, so that's equal to 4 by a0 cube. So we have to apply the product rule. The derivative of first function is minus 2 by a0 times e raised to minus 2r by a0 times r square. So first derivative of first function into second function plus first function into derivative of second function. So e raised to minus 2r by a0 times derivative of r square is 2r. Now let us take constant terms outside, common terms outside. So the common terms are 2r e raised to minus 2r by a0 is common. So what is remaining? In the first term we will have minus r by a0. In the second term all the terms are taken out, so plus 1. Now if we put this is d by dr of P of r. If we equate this derivative of probability, radial probability equal to 0, then this many terms should be non-zero, right? We cannot equate it to 0. So the only term equal to 0 is this much. So we have minus r by a0 plus 1 equal to 0. So from this we get r is equal to a0, and this r is the radial distance for maximum probability. Okay, in other words, this is the most probable radial distance from the nucleus. So when the electron is in oneness state, the most probable radial distance from the nucleus is a0. In other words, the plot of probability, radial probability, should be maximum at a0. Look at the plot given here in oneness state. This is maximum exactly at a0. Denominator in the x-axis, r is radial distance is measured in terms of a0, and this p corresponds to 1 time a0. Okay, and you can repeat this calculation for other states. Okay, you can do this as a homework. Take the table of radial probabilities are given in the textbooks. It is there in Kenneth Crane, table 7.1. In Arthur Beiser also, it is in chapter 6. Look at table 6.1. Okay, that gives you, yeah, it is in chapter 6. Look at table 6.1. That gives you I think the first 10, okay, states of a hydrogen atom. So you can take the radial wave function. We are interested in radial wave function here. Take the radial wave function and find this, write the expression for P of R. Okay, P of R is R square, capital R square times small r square. Then derivative, differentiate it with respect to R, equate it to 0. Then the probability will be maximum, and that radial distance corresponding to maximum probability is the most probable radial distance. So if you repeat this calculation, I am just quoting the result. If you repeat this calculation for n equal to 2 and L equal to 1, okay, that is 2p state, you will see that this R maximum probability is exactly 4 times A0. Similarly, n equal to 3, L equal to 2, that is 3D state. Here also the most probable radial distance, you can see it as 9A0. Okay, so there is a correspondence here with the Bohr model. Okay, when for a given n, okay, for a given n, when L is equal to n minus 1, the corresponding to the maximum value of L, okay, what you get is the most probable radial distance, or the radial distance corresponding to maximum probability is n square times A0. For n equal to, for 1s state, for n equal to 1, L equal to 0, it is A0. For 2p state, here also the highest value of L is 1. Okay, we are taking the highest value of L. 2p state is 4A0, that is n square, 2 square A0. For 3D state it is 3 square A0, 9A0. So for a given n, if you consider different L state, the L state corresponding to maximum value of L, that is n minus 1, this shows the most probable radial distance exactly as n square A0, which is the radius for the Bohr orbit. Okay, for each orbit in Bohr model, the radius is given as n square times A0. So here the correspondence is that the most probable radial distance, that too, for there are different orbits for each n state, but if you take the highest L state, its orbit, the orbit with highest L value, its most probable radial distance is n square A0. Let us again come back to our plots here. If you go to n equal to 1 state, 1s state, we see that it is probability is maximum, radial probability is maximum at A0. For n equal to 2, you look at 2p state. We know that it has only one antinode, and this antinode is exactly at 4A0. 3D state, again there is only one antinode, and this is exactly at 9A0. Okay, so this shows this type of a variation. And what is the reason for this? The reason is that in the expression of the radial part of the wave function, the radial wave function, there is certain symmetry. Okay, we can write the general form of the radial part of the wave function like this. See, for n equal to 1, L0, okay, we can write R10 proportional to R raised to 0 e raised to minus R by 1A0. Okay. For n equal to 2, L equal to 1, we are taking the highest L value. Okay, that is R21. This is proportional to R raised to 1 e raised to minus R by 2A0. N equal to 3, L equal to 2, 3D state. Radial wave function R32, this is proportional to R raised to 2 e raised to minus R by 3A0. So you can verify this by looking at the table of wave functions. Okay. For example, table 6.1 in Arthur Weiser. if you are referring Kenneth Crane, look at the third edition. Okay, it lists us again the first 10 or so wave functions, and look at the radial wave function for these three cases: 1s state, 2p state, and 3d state. The radial wave function shows this type of a symmetry. Okay, so if you generalize, okay, in general I can say, so in general, if you have r, n, principal quantum number is n, and orbital quantum number is n minus 1, the highest orbital quantum number for a given n, then this is proportional to r raised to n minus 1 e raised to minus r by n times a0. Okay, this is the form. If you generalize from these three cases, if you generalize for the nth state, the power of radial variable will be n minus 1 here, and in the exponential part n appears here in the denominator of the exponential factor. Now let us find out what is the radial probability in this case. So the radial probability is proportional to, we know that it is proportional to capital R square times small r square. So if you take the product with the small r square, you have r raised to n minus 1 here. Okay, so if you take the square of this one, you will have we have r raised to 2n minus 2 and e raised to minus 2r by na0. This is r square times small r square, that is the probability, okay, radial probability. Then this is proportional to, there is an r raised to minus 2 here. See, in this part you have an r raised to minus 2. It will cancel with this r raised to 2 here. So we have r raised to 2n e raised to minus 2r by na0. Okay. Now take the derivative of this radial probability. So this derivative is proportional to, the other factors are constant. Okay, so you have to do the product rule again. So this part will be 2n r raised to 2n minus 1. Okay, e raised to minus 2r by na0, then plus r raised to 2n times e raised to minus e raised to minus 2r by na0 times 2 by na0. Okay, now if you take common terms outside, we can take 2 r raised to 2n e raised to minus 2r by na0. Suppose we take this outside. Okay, then the first term will be n times r raised to minus 1. Okay, n times r raised to minus 1 if you take other terms outside, and the second will be minus, we get 1 by na0. Okay, so in order to find out the most probable radial distance, we have to equate this derivative of probability equal to 0. Now if you equate that, these terms, including the constant and these terms will be non-zero. So this part will be 0. Okay, so we get n by r minus 1 by na0 is equal to 0. Or we can say r maximum probability equals n square a0. See, if you rearrange the terms, what you get is maximum, the most probable radial distance is n square a0. So this result comes because of the symmetry in the radial wave function. The radial wave function for the not all radial wave functions, for a given n, the radial wave function for the highest angular momentum state, that is L is equal to n minus 1. That shows this type of a symmetry, r raised to n minus 1 proportional to r raised to n minus 1 e raised to minus r by n is 0. So that is why the most probable radial distance, if you do this calculation, you get n square a0. So this is the first feature of this radial probability that we wanted to explore, the most probable radial distance. So what we see is that for each n, if you look at the L state with the highest value, okay, it is 1s, here 2p, okay, and here 3d. It will be having only one antinode, and the position of that antinode, that is where the probability becomes maximum, radial probability becomes maximum. This maximum probability happens exactly at n square a0 for this angular momentum state with the highest value of n, that is L is equal to n minus 1. As the second feature, let us consider the average radial distance. Let's again consult this plot. See this marker on the horizontal axis gives the value of the average radial distance. For 1s state, this we have done as a problem previously in the previous class. The average radial distance is 1.5 a0 as shown in this figure. We have done the calculation also, 1.5 a0. When you go to the next states, 2s and 2p state. For 2s state, from the figure, you can do this calculation once you know the radial wave function. For 2s state, it is 6 times a0. For 2p state, it is 5 times a0. So these values are close, okay, even though for s state, the average radial distance is greater. That means electron in 2s state spends, there is more probability of finding the electron away from the nucleus. So its average radial distance is higher. Okay. So it is 6a0. This is 5a0. So it's roughly, we can say, some 5.5a0, the average radial distance for the two states, for n equal to 2 state, whereas this is 1.5a0. So the average radial distance in n equal to 2 state, for if you consider the two angular momentum states together, this value, these two values are nearly 4 times higher than the value here. Okay, and when we come to n equal to 3 state, these three average radial distance, again s state, 3s state has higher average radial distance, around 13, let us say 13 a0. 3p state has nearly 12 a0, and 3d state has nearly 10 a0, but these values are again close together, and roughly this value is again some 9 times higher than this value, 1s state. Okay, so we can say that the average radial distance increases with the principal quantum number n, roughly as n square, proportional to n square a0. Okay, if this is roughly proportional to n square, if this is nearly 1.5 a0, this is nearly for in 1s state it is nearly 1.5 a0. It's exactly 1.5 a0. For 2s and 2p states together, it's nearly some 5.5 a0, some 4 times higher. For 3s, 3p and 3d states together, it is nearly some 12 a0. Okay, 9 times higher than this value. So principal quantum number decides not only the energy, but it also decides the average radial distance from the nucleus. Okay, and for each n, we can say that the s states will be having higher average radial distance. Okay, so we can say, so for each n, the average radial distance for s state is greater than average radial distance for p state, which is greater than average radial distance for d state, etc. Okay, if such states, s state, p state, d states are all available, then as in the case of this one, 3n state, Okay, for S state it is greater than P state, then it is greater than T state, but still these values are close together, and roughly the average radial distance varies as n square, we can say. Okay, for average radial distance varies as n square, roughly, not exactly. Okay. As a third feature, we are considering the probability for the electron to be found within the Bohr radius. See, in Bohr model, the idea is that the orbits of the electrons are all fixed. For example, when n equal to 1 state, the electron is revolving around the nucleus through A0, an orbit of radius A0. That is called first Bohr orbit, or that radius is called Bohr radius. If n is equal to 2, it is 4 times A0, n equal to 3, 9 times A0. So these Bohr orbits whose radii are vary with n square A0. But in the case of quantum mechanical model of the hydrogen atom, the electron has a probability to be found within the Bohr radius also. So let us do this calculation for n equal to 1 state. 1 state. Okay, so for n equal to 1, that is L equal to 0 state, that is 1 state, what is the probability for the electron to be found within the Bohr radius? So here the radial wave function is, we have quoted it earlier, 2 by A0 raised to 3 by 2 e raised to minus r by A0. Okay. So let us start with the probability for the electron to be found between r and r plus dr. Okay, this value is mod r square, small r square dr. Okay, so let us take the square of this radial wave function. So this is 4 by A0 cube e raised to minus 2r by A0 r square dr. Okay, this is the probability for the electron to be found within a spherical shell of distance r to r plus dr from the nucleus. Then what is the probability for the electron to be found within the Bohr radius? That means between 0 and A0. So this is obtained by integrating this from 0 to A0. So 4 by A0 cube. Okay, let us take the constant terms outside. So 4 by A0 cube integral r square e raised to minus 2r by A0 dr. So let us do a change of variable here. So let me put this 2r by A0, that is the factor in the exponential, this factor in the exponential this power here. Let us take it as some variable, let us say x. So we have r is equal to A0 by 2 into x. So the limits will be r equal to 0 means x is equal to 0, but when r is equal to A0, x is equal to so what you get when you put r is equal to A0, x is equal to 2 we have. Okay, right? So that integral will become probability to be found between 0 and A0 is 4 by A0 cube integral 0 to 2. The limits are for the x. Yeah, so r square becomes A0 by 2 whole square times x square. So instead of r square, I can substitute A0 by 2 into x square e raised to minus x, right? 2r by A0 I have substituted for x. What is dr? From here, dr is equal to A0 by 2 times dx. So dr is A0 by 2 times dx. So this A0 by 2, if I take outside, A0 by 2 square into A0 by 2 is A0 cube by 4. So that will cancel with No, A0, yeah, A0 cube will cancel, 4 will cancel. We have 1 by 2 integral 0 to 2 x square e raised to minus x dx. Okay, so we have to integrate this. For this we have to do integration by parts. Okay, so it is half. We can take this x square as the first function, e raised to minus x as the second function. So we have first function into integral of second function uv within the limits 0 to 2 minus integral v du. V is integral of second function, so we have a plus here, e raised to minus x 2x dx. Now opening the brackets, when you put the upper limits, we get minus 4 e raised to minus 2. When you multiply with the 1 by 2, we have minus 2 e raised to minus 2. The lower limit will give 0 value because x square becomes 0. Then plus half, half and 2 will cancel. Okay. So the integral will be integral 0 to 2 x e raised to minus x dx. Okay. Again we can do integration by parts to the second integral. So minus 2 e raised to minus 2 plus uv minus integral v du. Okay, again e raised to minus x, du is dx. Okay. So we have, opening the brackets, minus 2 e raised to minus 2. Again lower limit will give 0 value, and here the integral is minus e raised to minus x within the limits 0 to 2. Okay, so we have minus 4 e raised to minus 2, and this is minus e raised to minus 2 minus of plus 1. E raised to 0 is 1. So minus 5 e raised to minus 2 plus 1. So if you substitute, what you get is 0.323. Okay. So the probability for the electron to be found between 0 and A0. Okay, 0 and A0 is 0.323. If you convert this into percentage, it is 32%, nearly 32%. So it means that if we make 100 measurements, nearly 32 times, when the electron is in 1s state, if you make 100 measurements for electron's positions, nearly 32 times the electron will be found between 0 and A0. Okay, it can also be found beyond A0 also, right? See, the nearly 68 times the electron will be beyond A0. So more probabilities for the electron to be found beyond A0. We know that from the figure, again going back to the figure of the plot of the radial probability density. Look at the first figure here. We know that the most probable radial distance is A0. But there is some, the area under the curve between 0 and A0 is, we will get 32% of that, 0.32. So beyond A0 is 68% probability, 68 times we will get that. So the when you take the average will be greater than A0, and the average is 1.5 A0. Okay, so the point is that even in the ground state, in the 1s state, there is a significantly large probability for the electron to be found between the nucleus and the first Bohr radius. Okay, Bohr radius, first the radius of the first Bohr orbit, 0 and A0. We can repeat this calculation for other states. Okay, I will quote the result. So this probability in the case of 2s state, n equal to 2, L equal to 0, 2s state, the probability for the electron to be found between 0 and A0, you can repeat the calculation the same way. You can try that. 0.034. Okay, it decreases, and when you go to 2p state, this probability for the electron to be found between 0 and A0 is 0.0037. Okay, this is 10 times smaller. So if you compare these two, when the electron is in 2s state, the probability is 0.034, only around 3% probability. If it is in 2p state, is 0.0037, about 0.37, one tenth less. Okay, 10 times smaller. So this probability, when you go from 1s state to 2s state to 2p state, this probability for the electron to be found between 0 and A0 decreases. Between 2s and 2p state, for 2s state the probability is some 10 times larger, 2p state is less. Okay, again you can see this result from the plots of radial probability. See here, for 2s state you can see that there is a peak here. Okay, so there is an area, some significant area under this curve. So between 0 and A0 there is some probability, some 0.3, okay, some 3% probability, right? Some 3% probability is there. Whereas for 2p state, the area between 0 and A0 will be very less. Okay, it's only very small, some 10 times less. So we can say that this trend is there for each n state. For each n state, the lower the value of the L, the angular momentum state, that means S, L equal to 0, L equal to 1, etc. The lower the value of L, the probability to be found within the Bohr radius, within between 0 and A0 will be higher. Okay. Whereas as L increases, this probability decreases. We have seen this in the case of 2s and 2p. So the curious case for example, 2s state. 2s state, what you see is that the probability to be found between 0 and A0 is higher than that of 2p state. At the same time, from the figure you can see that the probability to be found beyond A0 is also higher in the case of 2s state. So that the average value is higher in the case of 2s state. Remember that in the previous feature we have seen that the average radial distance is higher for lower angular momentum states. So for lower angular momentum states, there is a higher probability to be found close to the nucleus between 0 and A0, and also there is a higher probability to be found away from the nucleus. That is why the average radial distance is higher. For 2s state is 6 times A0. Whereas for 2p state, the probability to be found near to the nucleus is less. Away from the nucleus is less than that of 2s state. That is why its average is only 5 A0. So this S state electron, or we can say lower angular momentum state electrons, in each n, the lower angular momentum states electrons spend more time near to the nucleus and also more time away from the nucleus. The probability to be found near to the nucleus is high. Probability to be found away from the nucleus is also high. The second factor is also high. That is why the average radial distance is high for lower angular momentum states. So how do we explain that in a particular angular momentum state, the probability for the electron to be found close to the nucleus is also high, away from the nucleus is also high? In order to understand that, we can look at the shape of the orbit, how the shape of the orbit varies with angular momentum. Now, if we consider the classical orbits of a particle, for example, the orbits of planets around the sun, for a given energy, as energy varies, the average distance from the from the center, that is from the sun, also varies. So for a given energy, different types of orbits are possible. Okay, for example, for the same energy, orbit of the planet can be nearly circular, as in the case of, suppose this is a position of the sun, so orbit can be nearly circular as in the case of the earth, or it can be an ellipse, a larger ellipse, or a more elongated ellipse. Okay, or it can be a highly elongated ellipse like this, as in the case of a comet. Okay, so for all these orbits, the energy is the same. Energy is the same. Total energy is the same. Now, what is the difference is with the shape of these orbits, the angular momentum value will be different. For this circular orbit, L is maximum for the circular orbit, and for the highly flattened ellipse, the angular momentum is minimum. Okay. Now we can see that if we look at this highly flattened orbit, um, here, if you consider a planet or a comet moving around the sun in this highly flattened ellipse, then it spends more time. The probability to be found very close to the sun is high compared to the planets in other orbits, and the probability to be found away from the sun is also high. It spends more time near to the sun and also away from the sun because of the flattened or flattened elliptical orbit. So this is a feature for classical orbits of planets and comets around the sun. Okay. For circular orbit, angular momentum is for a nearly circular orbit of a fixed radius, angular momentum is maximum. For a highly flattened ellipse, angular momentum is minimum for the same energy. Okay. Now the electrons orbit around the nucleus in hydrogen atom share the same feature. For the same energy, that means for the same principal quantum number, different angular momentum states are available. Now, see, if angular momentum is maximum, then the orbit will be nearly circular. Angular momentum maximum means for each n you have angular momentum values from 0 to n minus 1. So if angular momentum is n minus 1, okay, angular momentum state is n minus 1, the orbit will be nearly circular. If the angular momentum is minimum, that is 0, then the orbit will be highly flattened ellipse. So in such cases, when L decreases, angular momentum quantum number is very small, then the probability to be found near to the nucleus between 0 and A0 will be high, and also away from the nucleus is also high, so that the average radial distance for such states will be high. This we have seen in the plots of radial probability. So this is the reason why for each n, the lower angular momentum states like L equal to 0 state will be having higher probability to be found within the first Bohr radius between 0 and A0, and also their average radial distance is also high. That means they have a higher probability to be found away beyond A0 also. Away from the nucleus also their probability is high. Whereas if L is equal to n minus 1, angular momentum quantum number is equal to n minus 1, the orbit is nearly circular. That means L equal to n minus 1 orbit, the orbit corresponding to L equal to n minus 1 state, behaves nearly like a Bohr orbit in Bohr model. This is the reason why when L is equal to n minus 1, when you look at the plot of the radial probability, it is having only one antinode, and that antinode, that most probable radial distance, is nearly n square A0. The reason is that the orbit is nearly circular, and it behaves nearly like Bohr radius for L equal to n minus 1 state. Okay, so this is the reason why for each n, different angular momentum states show this variation in radial probability. Okay. So with this we can end the discussion on radial probabilities of the electron around the nucleus. So we have considered three features of this radial probability. One is the most probable radial distance. Okay. Second is how the average radial distance varies between different angular momentum states, and also how the probability for the electron to be found within the Bohr radius, how this probability for the electron to be found very close to the nucleus varies in different angular momentum states. And these three features can be deduced graphically from the plots of the radial probability. Okay.